Hey everybody, Dr. Retzik here with you. This is our third and final video in section 16.3. Let's get started. I thought we could do one more example just to make sure all the pieces of 16.3 are in place. So here it is. Example. We need to compute integral over the curve C of 2x over y dx plus quantity 1 minus x squared over y squared dy, where C is the following curve. They're going to show us a picture of it. So this is good old XY plane. You can see this problem's 2D rather than 3D. And the curve is going to start here at 1 over 2 up. And then it's going to go around for a while, and then it's going to end here at 5 over 3 up. So this is the curve, like so. So this is the point 1, 2, and this is the point 5, 3. Okay, so that's what we're being asked to do. Now, the first thing I observe in this example is the form of the integral looks slightly different, and we really need to interpret it as a good old line integral f dot dr. So you see this notation sometimes out in the world, and you have to know that they just mean, since this piece right here means x prime of t dt, and this piece right here means y prime of t dt. It's just pixels. They literally mean that. Then this thing looks like a dot product. It looks like this comma this dot this comma this. So it really is f dot dr. It's just written a little bit in disguise. So it's something we're prepared for. So really we're doing this. F dot dr, where r represents whatever parametrization of that curve, and f is a 2D vector field, which is, what was it? It was 2x over y, first entry, 1 minus x squared over y squared, second entry. Now, you can see that that vector field is problematic when y is equal to 0. It's okay though, because our curve stays away from the x-axis, so we could imagine the domain for this guy being, say, this region here. And if that is our region, call it D, if that's our domain, well, that domain is clearly really nice, no holes, connected, open, etc. So we just have the standard setup now. So fundamental theorem of line integrals is in play, provided we could figure out if f is somebody's gradient. So the question now becomes, is f somebody's gradient? Is big F equal to the gradient of little f for some differentiable function, little f? So we have this question. Now, we could just launch into trying to find little f, or we could look before we leap and make sure that little f is there to be found. Remember, this is m, and this is n, And if m is meant to be little f's x partial and n is meant to be little f's y partial, then those mixed partials from Clairaut would have to match. So we would need dm dy to be the same as dn dx. And if you take those two partials, you find they indeed do match. dm dy, well, what is that? That's negative 2x over y squared, which is dn dx. So they match. So by component test, we know there's a little f to be found. Remember, component test is much simpler in 2 dimensions than in 3 because there are fewer mixed partials to check. Okay, so we know this. We know that big F really is the gradient of some little f. And then by fundamental theorem of line integrals, this is going to be an easy integral to do. It's just going to be f at 5, 3, take away f at 1, 2. Fantastic. So all we have to do is find little f now. And once we do, we'll plug those 2 points into little f, and we will win. Okay, so let's go find little f. Finding little f of xy. Now, this example has some added value in it based on our class discussions. Let's look at this here. Well, little f, so 2x over y is supposed to be little f's x partial. So that means little f, well, at the very least, you got to have an x squared over y, but then you might have some stuff with y's in it as well. But certainly, if little f looks like that, the x partial is correct. But then if you want df dy to equal what it's supposed to, so 1 minus x squared over y squared, well, okay, hang on a sec. Look at the left-hand side of that equal sign, df dy. This is f right here. So df dy, differentiate that with respect to y. So you get negative x squared over y squared. Remember, x is a constant as far as y is concerned, plus h prime of y. That second bit has no x's in it, so partial with respect to y of that bit is just a regular old derivative. So we need all that to equal 1 minus x squared over y squared. That's what we need. So this side is this, and this side is this, and we need them to be equal. Now you can see algebraically that this problem has a little twist that some of the examples from class didn't. This and this cancel, and so you need h prime of y to be 1 over y squared. Now this is different from some of our earlier discussions because in those, everything already matched on both sides of the equal sign, and so that extra derivative was supposed to be 0, which meant the extra function h of y was supposed to be constant. Not here. We need h prime of y to be 1 over y squared for all of this to match up. All right, so that implies that h of y must have been minus 1 over y plus c. And now that we know that, we can return to this box here and find out little f's true nature. Therefore, little f of xy, the potential function that we know is there to be found by the components test, must be x squared over y, take away 1 over y, plus c. Okay, so now that we have little f, this is it. We win, because if you want to do the line integral of f dot dr over that original curve, well, that's just the line integral of gradient f dot dr over that original curve, which is nothing other than f at the endpoint 5 over 3 up. Take away f at the starting point 1 over 2 up. Let's do f of 5, 3, that's 24 thirds. So 8. Take away f of 1, 2, which is 0. So the answer is 8. Now, here we used c equals 0. If you prefer c equals 17, that's fine. This would just read 8 plus 17, take away 0 plus 17. So 17s would cancel anyway. So we may as well use c equals 0. Okay, so that's it. When there's a potential function little f to be found, you go and find it, and then it makes line integrals much, much easier by a fundamental theorem of line integrals. Okay, that's it for 16.3. You have the tools now. You know what it means for a vector field to be conservative, and you know the implications that has on computation of line integrals. All right, see you next time.